So this is where we make them. It's about a 10-minute drive from here in Sunnyvale, sort of over where, if you know where NetApp is, we're like 2 blocks from NetApp. And that's where we build them. This is a bunch of them getting ready to ship. And the black coating is an anti-fouling paint. It's got a lot of copper in it. And most sea organisms don't like copper. So things like limpets and such, they don't grow on copper very well. So you can see they've got the solar cells on top. This little mushroomy kind of thing is the main GPS antenna and the iridium antenna. This tall thing up here, this is a weather station. And this is another satellite antenna that we don't use very much, but it's even more expensive, but it does bulk data. And these guys actually all have cameras on them. And the cameras, these cameras are mounted to look to the side, because these ones are designed for looking for oil spills. And they've got, these guys have got instruments called fluorometers on them, which are capable of detecting different kinds of oil. They can detect algae and that sort of stuff. And then the side-mounted camera is for taking these sort of oblique photographs of the oil films, because the oil floating on the water gives you a particular sheen. And one of the things that's been sort of interesting, and the reason that the cameras are there, is that when you look from a satellite down to see whether or not it's an oil spill, you can't tell very much about the oil. And so, like in the Gulf of Mexico, there's like naturally percolating bits of crude oil. You get these things that look like large oil spills from a satellite, but they're actually places where there have been mass quantities of fish. That, say you get like an algae bloom, and then you get a lot of krill that grows, and then you get a lot of fish that go there, and the fish go wild, and you'll get like several square miles of just like wild fish. And of course, the fish exude oil. So you get a layer of fish oil on the top, which satellites can't tell the difference between an oil spill and happy fish. Whereas we can tell the difference. So these things are really, really tough. They can go through high seas, and that's actually one of the really cool things. These guys go through hurricanes. These charts right up here, these are from one of our wave gliders just off the coast of Australia. About the high point here is roughly New Year's Eve. And if you can read, this is wave height in meters, so it got up to 30-meter waves, and winds of 91 knots, which is a little over 100 miles an hour. So this is your basic hurricane, although it's in the Pacific, so they don't call them a hurricane. And one of the nice things about being wave-powered is that you kind of like waves. And everything has been built so that these guys can go through hurricanes without very much in the way of issues. Like when Sandy was hitting New York, we had gliders underneath. It's interesting looking at animated maps of the Gulf of Mexico, because the hurricanes come through the Gulf of Mexico, all the ships leave, and the only craft left in the middle of the Gulf of Mexico are our little robots. And they just keep chugging on. They just love the waves. And they occasionally tangle with sharks. So here are some pictures. This is one that got his tail kind of chomped. And the shark, this is a very large shark. As you can see from how far down the wings the tooth bites got. And amazingly, mostly what he did was just scratch the paint. This little triangle here, that's a fragment of his tooth. We pulled this one cable out of its protective housing. We've had like a long string of experts look at that tooth fragment. Nobody can figure out what kind of shark it is. And all except for one little problem, which is we had one place where we've got like 2 inches of exposed cable, and a tooth sliced the cable, and we lost control of the rudder. So this guy was drifting a couple 100 miles off the shore of Maui, and we had to send somebody out to get him. So what do you do with these things? They can act like a weather buoy that installs itself. So if you think of like a buoy out in the middle of the ocean, you'd think that they're kind of inexpensive because they just sort of float there and they got some instruments on top. But the ships that go out to do servicing missions on them cost about $150,000 a day to operate, and it takes like a week out, do your thing, a week back. It can be a couple $1 million just to do one servicing mission on a buoy, and you service them once a year. It adds up to real money pretty quickly. Our little guys, you literally throw them off a pier in deep water. They'll swim out to the middle of the Atlantic. They'll sit there doing donuts for months and months and months and months. Every now and then you have them swim back to shore. Somebody scrubs the barnacles off, and out they go again. And they just sort of drive themselves back and forth, and it works really nicely. We do a bunch of work with oil and gas folks. One of the interesting things you can do with these wave gliders is that since it's there like on the water surface, they can communicate with a satellite, but they can also use acoustic modems. You remember the old acoustic modems when you had phones and you'd put them in the foam rubber couplers? That's exactly what happens here. It even sounds the same, and that's the way that you communicate with things underwater. So whether it's submarines or buoyancy gliders or various sensors on the ocean floor, like one of the things one of the kind of sensors that's fairly commonly out there is these sensors for tsunamis. You can't sense a tsunami just by sitting there and watching the water surface, because a tsunami doesn't actually rise very far. It's a very large wave, but it's not a very tall wave. So what you do is you put a gravitometer on the bottom of the ocean, and you measure the distortion of the Earth's gravitational field. And that's the way you detect a tsunami. The problem is that the sensor is on the bottom of the ocean. So how do you get the data out? Traditionally what you do is you run a really long wire, and it has to be like a piece of wire that's like a couple 1,000 kilometers long, because if it's not that long, if it's not that far offshore, you're not getting that much warning. And those wires always break. So the vast majority of the world's tsunami sensors are broken. And our guys can just sort of sit over top of them and talk to them with an acoustic modem and yell and scream. We do pollution monitoring. That's a rig in the Gulf of Mexico. We can do marine mammal monitoring, and I had wanted to give you some real-time whale song, but it's not working today. And people do stuff where they put like a row of these things around like marine sanctuaries. Marine sanctuaries turn out to be a really popular place for fishing, because they're protected, so they tend to have a large, healthy population. So people with somewhat shallow morals just go in and harvest them. And usually these places will be like, hundreds of thousands of square miles, and there's just no way to patrol them. The Coast Guard's funding for patrolling all the marine sanctuaries around Hawaii is nowhere near up to the task. So we can do it a lot more economically. People do interesting global warming studies. So the summer before last, we did this big survey of water temperature and such in the Arctic. It's the biggest survey of the chemistry of the Arctic Ocean ever done, and the numbers were scary. So I'm mostly working on sort of two things. One is all the shoreside stuff, and also the guts of the next generation wave gliders. The current ones, you really don't want to know how those things work. The processor in them is a couple of notches above a smart card, but not a whole lot. The new generation has a lot more power and much better hydrodynamics. They've actually got a thruster. There's this sort of inverse correlation between sunshine and waves. You know, when there are almost no waves on the ocean, there's almost always a lot of sunshine. And we have a bunch of applications where people would like to have hundreds, even thousands of wave gliders. And currently, the way that we pilot these things, we just can't do masses of them. So we need to be able to have them do things like dodge ships on their own. Right now, they will do that in simulation, but the real ones won't do it yet. I'm hoping that within a few months, they will be dodging ships on their own. That's kind of job one for me. So this is the rig that I mostly work on these days. This is the guts of a wave glider sort of opened up, the electronics. So this right down here, this is a TI OMAP ARM processor. It's got, you know, the usual Wi-Fi and all the rest. One of the strange things about this whole industry is that it's one of the last places where RS-232 serial lines are everywhere. And it's really hard to find processor cards that have a lot of serial lines. And almost every piece of marine instrumentation that you can buy has a serial line interface. The standards body that sort of sets a lot of these communication standards, that they issued a new standard 13 years ago that's all about using the CAN bus. And essentially no one has transitioned to using the CAN bus. They're all still serial lines. Mostly they don't have any plans to be off of serial lines. So we have to do all this stuff with serial lines. You know, we'll put like a dozen serial lines on one processor, and it is a pain in the butt. So this is the guts of the Iridium modem. There's a GPS in here. This is batteries and power supplies, and so this is kind of the contents of the glider kind of opened up. Over on the left here, outside of the shot, is a bunch of antennas. And you know, it's got there's a GSM board and the whole 9 yards. So it's a pretty deluxe computing environment compared to what we had before.